In Lesson 2, we're going to look at fractional distillation, a method of separating the hydrocarbons in crude oil into useful fractions. Before we begin, I'd like you to recap the content from last week. So please read these questions, pause the video, have a go at them, and then come back to check and improve your answers. The definition of crude oil is a mixture of compounds called hydrocarbons. The definition of a hydrocarbon is a compound made from hydrogen and carbon atoms only. In order for a hydrocarbon to be classified as an alkane, it must meet two criteria. The first is all the carbon-to-carbon bonds are single covalent bonds, and the second is that it must abide by the general formula of CnH2n plus 2. This is the general formula of alkanes, and it means that the number of hydrogens is twice the number of carbons and another 2. So therefore, if an alkane had 6 carbon atoms, it would have twice the number of hydrogens plus 2, meaning that its formula would be C6H14. The name and formulae of the first 5 alkanes are as follows: methane CH4, ethane C2H6, propane C3H8, butane C4H10, and pentane C5H12. Let's have a look at the properties of hydrocarbons. We can say that hydrocarbons have different chain lengths. Their chain length is dependent on the number of carbon atoms they have, and it will influence their physical properties like melting point, boiling point, and viscosity, a measure of their thickness. We've drawn the first 4 alkanes here, and we can see that methane only has 1 carbon atom, so we can say it has the shortest chain length. As we increase the number of carbon atoms, the chain length gets longer and longer. It can get much longer than 4, it can actually go up into the thousands, but we're going to look at chain lengths up to about 70 today. Before we move on, I need us to understand boiling points a little bit better, because it's essential for understanding the process of fractional distillation, which we'll move on to later. Let's take a substance that we all know, like candle wax. Candle wax has a melting point of 70 degrees Celsius and a boiling point of 361 degrees Celsius. Candle wax, like most substances, can exist in one of 3 states of matter: lowercase s in brackets for solid, lowercase l in brackets for liquid, or lowercase g in brackets for gas. These are called the state symbols, or they denote the state of matter. The temperature at which a substance can change between a solid and a liquid is called its melting point, and the temperature at which a substance can change between a liquid and a gas is called its boiling point. Candle wax's melting point is 70 degrees Celsius, and its boiling point is 361 degrees Celsius. If we had candle wax at a temperature below 70 degrees Celsius, then it would be a solid. If we heated it above 70 degrees Celsius, its melting point, then it would melt and it would change into a liquid. If we heated it further so that its temperature was above 361 degrees Celsius, then it would evaporate and it would change into a gas. Cooling it back below 361 degrees Celsius but still above 70 degrees Celsius would cause it to condense, turning back into a liquid. And cooling it below 70 degrees Celsius again would cause it to freeze or solidify back into a solid. It's important that you know these changes of state shown here and be able to apply the temperature ranges to denote which state of matter that it's in at a given temperature. Now let's try to relate this to hydrocarbons by comparing their chain length versus their boiling point. The first hydrocarbon, methane here, only has 1 carbon atom, so we can say that it's got a very short chain length. Short chain lengths give a very low boiling point, in this case minus 163 degrees Celsius. I'm going to plot this to this graph over here, which shows the number of carbon atoms or chain length on the x-axis and the boiling point on the y-axis. 0 is here, negative extremely low boiling points go down, and positive increasing boiling points go up. So I'll plot this to the chart here. You can see that as we increase the number of carbon atoms, or the chain length, the boiling point is actually increasing. This might look a bit confusing to begin with because it looks like this number's decreasing, but remember that these are negative numbers, so it's becoming less and less negative, so it's actually an increasing boiling point. Increasing further shows this trend. So, we've gone up to C10, and we can see a clear relationship between the number of carbon atoms and the boiling point. But remember that the hydrocarbons in crude oil don't just end at C10H22. We actually go up to about C70, where the boiling point is way up at 600 degrees Celsius. So, we've got increasing chain length and increasing boiling point. So we can say that the longer the chain length, the higher the boiling point, or the higher the temperature you would need in order to evaporate a hydrocarbon. Viscosity is a measure of the thickness and gloopiness of a substance, and we can say that the longer the chain length, the higher the viscosity. This is especially important when choosing a fuel for an engine, because you wouldn't want to put a fuel that has too high a viscosity, too thick and gloopy, in an engine where it could block up the pipes. Flammability follows the opposite trend. We actually find that the shorter the chain length, the higher the flammability. So short chains like methane are very, very flammable, whereas longer chains like C70, for example, have very low flammabilities. So we could also say that the longer the chain length, the lower the flammability. In task 1, I want you to apply what we've just learned by describing the properties of hydrocarbons based on their chain length. Read these questions, pause the video, have a go, and then come back to see if you got them right. The relationship between chain length and boiling point is the longer the chain length, the higher the boiling point. Viscosity is a measure of the thickness of a substance. High viscosity means it's very thick and gloopy. The relationship between chain length and viscosity is the longer the chain length, the higher the viscosity. The relationship between chain length and flammability is the shorter the chain length, the higher the flammability. But of course you could have gone for the longer the chain length, the lower the flammability. Let's compare chain length, boiling point, viscosity and flammability of propane with a short chain versus decane with a slightly longer chain. Propane has a shorter chain length and therefore it has a lower boiling point. It will also have a lower viscosity, but it will have a higher flammability. Decane has a longer chain length, therefore it will have a higher boiling point. It will also have a higher viscosity, so it will be more thick and gloopy because of its longer chain length, but it will be less flammable because of its longer chain length. There's some more questions here, and I want to explain them before you attempt them. For each substance, I've given you its melting point and its boiling point. Pay careful attention to see if that number is a negative number, because it is in some cases. I've given you a temperature, and I want you to tell me what its state of matter is at the given temperature. So basically, your answer should tell me whether it's a solid, a liquid, or a gas at this temperature when given the melting and boiling point data. Pause the video, have a go at the questions, and then come back to see if you got them correct. I always find determining the state of matter easier if I plot it to a little chart. I first write S, L and G for solid, liquid and gas. Because these are state symbols, we need to draw these in lowercase. Capitalised state symbols would not be accepted. We're then going to plot to this the melting point of minus 188 degrees Celsius and the boiling point of minus 42. We're then going to plot the given temperature to this chart. 25 degrees Celsius is above minus 42, so we plot it to the right and it lands on G for gas, because we're above its boiling point. We'll do the same now for decane. The given temperature of 100 degrees, it's not higher than 174, so we're not going to plot it here. It's lower than 174, but it is higher than minus 30. So therefore it goes around here somewhere, 100 degrees, so therefore it's a liquid, because the given temperature is between its melting and boiling points. Let's now do the same for butane. Minus 200 is less than minus 138, so it goes to the left of it over here. So therefore we're looking at a solid because the given temperature is below its melting point. Remember that crude oil is a mixture of compounds called hydrocarbons. And because it's a mixture of those hydrocarbons, we're going to have all of the different chain lengths present in the crude oil. The different chain lengths each bring with them different properties. So within crude oil, we're going to have some chain lengths that are shorter with really low boiling points, and other chain lengths that are longer with really high boiling points. We'll have some that are very flammable and others that are not so flammable. And we'll have some that have really high viscosities and some that have really low viscosities. So we've got all of these different properties kind of merged into one when we've just got the bulk crude oil in front of us. However, each of these different hydrocarbons within crude oil can be used for fuel. Within crude oil, we'll find hydrocarbons which are suitable for fuel for cooking, others which are suitable for fuel for cars, fuel for planes, fuel for lorries, and fuel for ships. However, crude oil in its raw form, because it contains all of the different chain lengths, each with their own individual properties, is not useful. You wouldn't just be able to put crude oil into a gas stove, because crude oil is way too viscous containing those longer chain lengths as well. It would block up the pipes in all of these engines pretty much, probably apart from the ship, which is used to taking very long chain lengths for fuels. You may find that some of the chains that are really long, because they're not very flammable, you wouldn't be able to put them through a gas stove because they simply wouldn't burn. Likewise, in a ship which is used to taking fuel that's surprisingly not that flammable, well, if you had the short chain lengths in crude oil, they'd be way too flammable for the ship's engine, so they'd probably blow it up. Therefore, what we need to do is somehow take the crude oil mixture and separate it into useful fractions. And here's a key word for you: fractions. A fraction is a smaller submixture of the crude oil, which contains hydrocarbons with similar chain lengths and therefore more similar properties. So, let's say for example our fuel for cooking, which is known as natural gases. Well, the fraction that is natural gases of crude oil only contains chain lengths between 1 and 4, which means that they're not very viscous, they've got very low boiling points, and they're very flammable. Fuel for cars is called petroleum. And petroleum has chain lengths between C5 and C10. So a slightly higher boiling point, slightly less flammable. Planes use a fraction called kerosene, where we take the hydrocarbons of chain length C11 to C14. That's an estimate for kerosene, by the way. Lorries take diesel, and diesel has chain lengths between 14 and 20. And fuel for ships is called fuel oil, which has chain lengths between C20 and C70. You can see that they, having longer chain lengths, would have much higher boiling points and would be way less flammable, but they're suitable for the engine on a ship. So, we need to separate the crude oil into fractions where the chain lengths are similar enough to work with the device you're trying to burn it in as a fuel. Fractional distillation is the method we use to separate crude oil into the useful fractions which can then be used as fuel. Here I've shown a fractional distillation plant, and it's comprised of two key apparatus. The first being a giant boiler, and the second being this tower, which we call a fractional distillation column. The first stage in fractional distillation is to heat the crude oil up inside the boiler until all the hydrocarbons that the crude oil contains evaporate, change into a gas. Here we can see the crude oil going into the boiler. Inside the boiler it's very hot, and therefore all of the hydrocarbons evaporate. Next up, the crude oil vapours are pumped into a column, which gets cooler towards the top. Here I've shown a pipe from the boiler going into the column here, and we can see inside the column. I've shown on the right here a temperature gradient. It's very hot at the bottom and gets cooler the further towards the top that you go. Spaced at regular intervals going up the column are trays. The trays are here to catch any vapours that condense into a liquid, to stop them falling back down lower down the column. What we can say is that the longest chain lengths have higher boiling points. So therefore, if a long chain length went into the column, then it wouldn't need to be cooled down much for that temperature to be just below its very high boiling point, condensing it into a liquid. So therefore, let's first take bitumen, which has the longest chain length. Bitumen I didn't talk about earlier because it's not used as a fuel. Bitumen is used for tarmac for roads and pavements. It has chain lengths of 70 carbon atoms and larger. Bitumen, with its very long chain length and high boiling point, would pass into the column as a gas, and even where it's very hot, it would quickly cool down to below its boiling point, and it would condense into a liquid and then be drawn off through the pipes on the right. Fuel oil has the next longest chain length. It wouldn't condense right away as it enters the column because it would still be too hot down the bottom, so its vapours would rise up a little bit before reaching a zone of the column where the temperature is just below its boiling point. This would cause it to condense to a liquid, and it would collect in the tray rather than falling back down, and then it would be drawn off. Shorter chain lengths, however, have lower and lower boiling points, so they're going to need to be cooled down more to condense. It would be way too hot for them to condense down here at the bottom because the temperature would be above their boiling points. So, shorter chain lengths continue to rise further and further up the column until they reach a zone that is lower than their boiling point, causing them to condense to a liquid, catch in the tray and then be drawn off. So diesel's our next longest chain length. It would pass into the column but rise further as a gas. Then when it reaches a zone that's just below its boiling point, it would condense into a liquid and then be drawn off. Kerosene for planes comes next, rising even further because it's got an even lower boiling point, so it needs to be cooled more in order for it to condense to a liquid. It condenses on its tray and then is drawn off. Petroleum next for cars, rises even further up the column because its shorter chain length gives it an even lower boiling point, meaning it needs to be cooled down much more in order for it to condense to a liquid and then is drawn off. Natural gases' chain lengths are so short that their boiling point is really, really low, and actually even the low temperatures at the top of the column are not cool enough to condense the natural gases, so therefore the natural gases go in as a gas but just exit the top as a gas. Because each of these different fractions are drawn off and stored separately, we can say that we've separated the crude oil into each of the fractions that you see here. There are more fractions, hence the reason that I drew more pipes. However, we don't study these additional fractions at GCSE. In task 2, I'd like you to read these questions here, all about fractional distillation and a little bit of a recap on the properties of hydrocarbons. If you could read them, pause the video, give them a go, and then come back to check your answers. Crude oil cannot be used directly as a fuel in a car because it's a mixture of different chain lengths. The longer chain lengths present would be way too viscous, so therefore they could block the engine. And the longer chain lengths also wouldn't be flammable enough for the engine to function properly. So, because crude oil is a mixture of all the different chain lengths, it has all the different properties of all of the hydrocarbons present, so therefore wouldn't be useful for the design of a car engine, which is only designed to operate on chain lengths 5 to 10, petroleum. The process used to separate crude oil into its useful fractions is called fractional distillation, where a fraction of crude oil is a smaller submixture of the crude oil which contains hydrocarbons with similar chain lengths and therefore more similar properties, for example similar boiling points. The fractions of crude oil in order from lowest to highest boiling point are as follows. Natural gases have the lowest boiling point, followed by petroleum, kerosene, diesel, fuel oil, and then bitumen. The fraction of crude oil that's not a fuel, is instead used for tarmac, is called bitumen. And the fractional distillation process can be described and explained as follows. Crude oil is heated until all the hydrocarbons evaporate. Crude oil is pumped into a column, which gets cooler towards the top. The longest chain lengths have the highest boiling points, so condense near the bottom of the column. The shorter chain lengths have lower boiling points, so need to be cooled more to condense, therefore they condense nearer the top. And because the fractions are drawn off and stored separately, the crude oil has been separated. You do need to learn this description of fractional distillation, because it's regularly a 5 to 6 mark question which features in AQA examinations.